Okay, so we are going to start. Welcome to the next KubeCon session, KubeCon talk. My name is Piotr. I'm a member of program committee of this conference. I'm here to introduce the next speakers. So Guido and Rafael are working for Slack, where they designed and built and scaled a distributed database service based on Vitess. If you are curious how, please join me and welcome on the stage Rafael Chacon and Guido Iaquinti.
Hello, everyone, and thank you. We are so excited to be here and sharing our experience with all of you. And also for us, it's super cool to see so many people interested about Vitess. And I just want to ask you a key question. Who knew about Vitess before CNCF? Could you raise your hand? Cool. OK. Without further ado, just again a little bit more about me. My name is Rafael Chacon. I'm an infrastructure engineer at Slack, and I've been part of the team that took Vitess from a prototype to now being our main data store in production. As part of that, I also made a big amount of contributions to Vitess open source project, and now I'm a maintainer there. And now,
my name is Guido Iaquinti, and I work as site reliability engineer. Previously, I was one of the first SRE at Slack, where I designed and built the first implementation of Vitess. I'm now working for them again as freelancer for some special project. So the agenda for today starts with an introduction about our current database setup, and we'll then talk about what running database in a cloud world means. Jumping then on challenges of fault tolerance and isolation, key lesson, and then I hope we're going to have plenty of time for Q&A. So for who is not familiar with our product, here is our mission statement. Slack is where work happens. Slack is a new layer of the business technology stack that brings together people, application, and data. Let's now talk about our database setup. So first of all, MySQL is the primary storage and single source of truth for all our customer data. We currently run on two different sets of shards or infrastructure, what we internally now call legacy shard and Vitess. We are in the process of migrating our entire data set to Vitess, and we plan to complete this migration by mid or end next year. So due to time constraint, we are not going to go into much detail about why we are moving away from our previous architecture, or why we choose Vitess, or how does it work, as all of those topics have been already covered in few presentations that we link here in this slide. The TLDR is anyway that we wanted to support different sharding models that our product can benefit from, as well as work around some shard size limits, improve our inefficient resource distribution and operational overhead that was required to run the previous architecture. So legacy shard run on a pretty unique architecture. So it's a MySQL master-master setup archived via asynchronous replication. The sharding is done at the application level, and the only sharding key support is workspace or team ID. This architecture served us very well for several years of hyperbolic growth, but we knew that eventually we needed to change it. The Vitess shard topology uses a more traditional primary replical setup that is fully managed by Vitess. Here you can see a few of the statistics of our database tier that can give you a better overview of the scale that we are operating today. As today, we serve over 50 billion queries, with this data flowing from thousands of terabytes stored on thousands of database servers. And currently, we serve roughly 40% of those QPS with this new architecture, but we are targeting to reach 70% by the end of the year. At peak, we are serving several millions of queries per second. Let's now discuss what running database in a cloud world means. When we start a new project, we usually start with a small fleet of hosts. Like, the customization is easy. We can treat our infrastructure as pets. Each one can have like its own name. Each one can even serve a specific workload or even a set of tables. At this scale, when we make a change, we can fit that variation in our head. This is not ideal, but probably still OK. Again, all the change can fit in our head, so we're kind of good. Now imagine a similar situation, but at a much larger scale. What if you have 100 or 1,000 of database servers? At that scale, it's hard to keep track of those changes, as well as correlate them with performance regression, production issue, new releases, and so on. To avoid that, we should strive to adopt few of the concepts of immutable infrastructure, where, for example, instances are untouched after getting provision, configuration change only happen through reprovisioning those hosts, and no in-place patching is allowed. At that stage, technically, you can run with a read-only file system, and also like operation like SSH become useless. Of course, you need to invest in monitoring, logging, and troubleshooting tools to make this transition happen, but the benefits that are greater than the effort that you need to input. Let's now talk about instance failure. So how do we treat an instance failure event in a cloud environment? The good thing is that with a couple of clicks, or even automatically, we can reprovision a host. So should we trust an instance that fails us even once? If you're flying a plane and your engine fails, all bets are off. From that moment on, the plane is trying to kill you, and from that moment on, the plane is a problem of the insurance company. Your primary goal is to save yourself and don't care if the plane is not going to survive. And the same concept should apply to databases, especially in the cloud. When an instance fails, it can't be trusted. Just replace it. OK, this sounds good, but also challenging for few setup. Like, if you use network storage, you can simply just stop and start your instance, as your storage engine is decoupled from the compute engine. If you use an instance store, that's unfortunately different. Like, to do that, you need to complete a restore, and so download possibly terabytes of data from your last backup, decompress it on the host, then MySQL has to start and catch up with replication. And due to that, like, recovery time is mostly impacted by the available bandwidth that you have on your NIC. And despite that it's virtual, it's not infinite. Linked to this point, there is also the never-ending question about running a bigger number of small shards versus running a small number of big shards. So my personal answer is that it depends. It depends on your setup. It depends on your workload. It depends on your data set, and so on. So there are a few pros about running a higher number of small shards, like, for example, having like lower recovery time, like reduced blast radius, and also have like much distributed workload. And even at the host level, less contention. That is, in MySQL especially, is a big plus. But there are also a few cons of that, like you're going to have broader scatter queries, better chance to hit hypervisor noisy neighbor issue, and so on. Traditional data storage software treated data as durable as soon as it was flushed to disk. A new approach of durability is archived by copy the data to multiple machines and even geographical location. In this example, we have a replication topology with a master node and 3 replica in semi-synchronous configuration, all deployed in different data centers. We can fail over to a new replica when the master dies with no data loss. Or even a replica dies, let's simply reprovision it from scratch. And we can do that because we rely on semi-synchronous replication and those 2 settings. The first is the value in milliseconds that control how long the master will wait on a commit for acknowledgement from a replica. We set it to a very high number, technically infinite, as we never want to hack a transaction that hasn't been hacked by at least one replica. The second setting is the number of replicas that need to acknowledge that transaction. In this example, we are OK to just receive one hack, as it means that the data has been correctly replicated on a host in another physical location. Rely on the replication stream also allows us to loosen some of the disk durability setting. For example, we could technically turn off sync bin log and relax the InnoDB flash log setting. In this scenario, we use all buffered I/O for all the operation, which will give us much higher throughput and better latencies than the previous approach. An important disclaimer here, like you can safely do this only if you always throw away a failed node. But that's exactly what we suggest, so we're good. Let's now talk about how we run Vitess as Slack. So we run our database stack on AWS in multiple geographic locations. We currently run Vitess fully on EC2, but we are evaluating to move a few components to Kube, following the way of other teams as Slack. The tweet that you can see on the right is from last year, and a lot of things have changed since then. Vitess can anyway fill the gaps there, but in our setup, we're not there yet. Stateless components are deployed in autoscaling group so that we don't need to care if an instance fails or if it gets deprovisioned by Amazon. Our engineer only need to manage our stateful fleet, leveraging some custom tool that we wrote. Another interesting fact is that our stateless fleet run on MySQL 5.7 Percona edition, and that we use ephemeral storage on non-volatile memory that give us very high and stable I/O performance, despite the storage that they offer is only ephemeral.
So with that, I want to dig a little bit deeper into how we deploy Vitess at Slack and what did we learn along the way when it comes to fault tolerance and isolation at our scale. So first, I just want to do a very quick refresher of what the Vitess architecture looks like. I'm not going to enter into many details, but if you're interested about this topic, just reach out after the talk, and I'm happy to talk about it. So first, on the left, you have BT gates. BT gates are a stateless router that the application uses to talk to your Vitess cluster. From the application perspective, a BT gate looks just as you are talking to any MySQL instance. BT gates implement the MySQL protocol. Then on the top, you have this very important component for Vitess that is the topology service. The topology service contains all the metadata about your shards and the sharding information. So when a BT gate needs to find a shard in Vitess, it does that through information that comes from the topology service. And then on the right, you have BT tablets. BT tablets, you can think of them as a sidecar that protects MySQL from bad users in your application. And BT gates talk to the shards through BT tablets. And then also an important thing in Vitess shards is that there is a single master for a given shard, and that replicas are first-class citizens in a Vitess deployment. So if your application can tolerate stateless reads, they can specify this when they connect to a BT gate, and BT gate can serve traffic from your replicas in your MySQL cluster. So with that, how do you actually deploy Vitess in your infrastructure? The standard Vitess deployment looks something like this. First, it's really important to notice this distinction that there is global and local topologies. The idea is that in the global topology, you have the minimum information that is required to bootstrap the components. So for example, when a VT gate starts, the first thing that it does is that it asks the global topology, what is the local topology that I should be using moving forward? And from that moment on, it never talks to the global topology. And then you have this concept of cells. Cells are also a first-class citizen in Vitess. The idea is that you deploy all components within the cell, and the cells encapsulate a failure domain, and they should map to your data centers. So then within each cell, you deploy local topology, BT gates, and BT tablets. One important thing that is important to call out is that in Vitess, you can only cross the cell boundary when talking to masters of a shard. Given that there is a single master for each shard, it makes sense that the cells need to be able to find masters in other cells. However, it does not allow you to route replicas that are in a different cell. And this was a design decision that made sense when all data centers were in physically separated geographic locations. So how we map this deployment to our infrastructure as Slack? So as Guido mentioned earlier, we use AWS heavily, and our Vitess cluster is deployed on top of EC2. In AWS, EC2 is hosted in multiple locations around the world. And those locations are composed of regions with availability zones. The regions are separate geographic areas, and as you can see in that image, you can have a region in US East or North Carolina, Sydney, Tokyo, et cetera, et cetera. But within those regions, you have these availability zones. The availability zones are connected through low latency links. And the idea is that you can think of this as you have data centers that are physically separated but still close to each other. So it gives you the benefits of having different failure domains for your infrastructure, but not paying high penalties when it comes to latency to connect to data centers that are in different parts of the world. And when people deploy services in AWS, it is normal that they rely heavily in the concept of AZs. Normally, they deploy in different regions, but then within those regions, they deploy it in different AZs. And that's kind of what we did at Slack. And something to call out is that at this point, we have clusters in multiple regions, but for the sake of the example, I'm just going to use one region. Also, we deploy in multiple AZs, but to make this simpler, I'm going to show how we used to deploy a Vitess cluster in, let's say, US East 1 and using 2 AZs. So the first thing to notice is that we use console KV as the underlying backing log server for Vitess. In Vitess, you could use etcd and Zookeeper for this, but at Slack, we use console. And we deployed the global topology across all AZs in the region. Next, it's important to notice that data center that we are having for console, that is the default data center. This will be relevant later. Now, the next important thing to mention is that we deploy a single cell. This cell maps to the region, but across multiple AZs. And then within that cell, we deployed the local topology for the cell, but notice that we use the same data center as the global topology, meaning that we were sharing the same underlying infrastructure for console for both the global topology and the local topology. Last but not least, we deployed BT gates and BT tablets in physical different locations because they were spread across all the AZs, but from the Vitess perspective, they were part of the same cell. So how this compared to the Vitess standard deployment? I think there are two main differences. The first one is that instead of having a cell per data center, we were having a cell for the whole region. This does not seem that bad, but it ended up being problematic. You may ask, why did you do that? And the reason is that there was a fundamental limitation. As I mentioned earlier, in Vitess, you couldn't route between cells, between cross cells, when you were doing replica reads. When we were using AZs heavily, we needed that a BT gate in a given AZ was able to talk to another tablet that was in the same region, but in a different AZ. So basically, from the Vitess perspective, at that point, we didn't have any other option than using a cell that mapped to the whole region. Second, we were using the same log server for both the local and the global topology. This was just circumstantial. Slack was a complete different company 2.5 years ago, different scale, different tooling. So from a practical perspective, when we were starting to ramp up this in our production services, it just made sense to reuse the same console. The setup, for the most part, worked like pretty well, but in time, it surfaced some problems that I want to discuss now. So what happened when there was an issue in console? Well, you have a fire in the global topology, and you think, oh, this is okay because the global topology is not needed for serving queries, but because it was the same underlying console, it meant that you also had a fire in the local topology. To make our thing more complicated, because our cell span across the whole region, a fire in the console created a fire in global, created a fire in local, and also a fire that spread across all our AZs. And because when it rains, it pours, we also discovered some bugs in the local topology that affected our serving path, meaning that when we were in this situation, some queries were failing in our Vitess cluster. In a nutshell, a failure in our default console data center put us in a very bad state. So I think that Mr. MySQL couldn't have said it better. If Vitess top is in mind of you, it should be. And after this, it was definitely in top of mind for us. So what did we do to fix this? Well, for us, the most important part was to serve our customers. So we did everything that we could to make sure that these issues did not affect the serving path. So every time we discover a console problem due to our scale and then having unavailability in the local topology, we made the local topology more robust. And if you look in the upstream Vitess project, you will see many contributions from Slack making this more robust and more resilient. However, when you think about it, what we were doing is just taking a defensive programming approach. Every time you run into a failure, you try to make sure that that failure doesn't happen again in the future. But for us, this was not enough. And it was not enough because the combination of a single cell that is spread across multiple ACs, plus the fact that we were sharing the same underlying infrastructure for the topology, surfaced a fundamental problem in our deployment. And the problem was not that we were having issues scaling the console cluster or that there were bugs in the local topology. This should be business as usual for any company that is growing like really fast and that is constantly pushing the limits of its infrastructure. The problem was that those failures cascaded to other components without clear boundaries. So we stepped back and kind of like took like first principles approach and thought, what do we need to make our deployment more resilient? What we wanted was that when the unexpected happened, the blast radius was minimal. And for this, isolation is key. And here, we mean real isolation. For instance, in our case, it did not matter that we were already using multiple ACs if they were tightly coupled together. And I think in that image, like chips are like really good examples of isolation and bulk heading, but the analogy will be that we created like some bulk heading, but then left like a small hole at the bottom, and then it didn't matter, the water came through all those holes. The other thing that we think is really important is that you think about your dependencies. This might sound trivial, but it's not when there is fundamental complexity in the systems that you are operating. Also, when you take the fact that things are changing rapidly. It's also important to mention that you cannot overlook the fact that sometimes you are basically learning how these things all fit together, and the full mental model of your operating these services in production is not fully developed. But if you don't invest in this, it will bite you hard. In our case, it was console, but everyone should see like what are the dependencies that it is hard to see what will happen when failures in those dependencies cascade across your whole infrastructure. So what we wanted was kind of to have the standard Vitess deployment, but that was able to map to an AWS infrastructure. So you may think that this was an easy task, just adapting those changes, but in fact, it took a big amount of effort to revamp the Vitess topology to be able to have the concept of AZs. And so far, this has been one of like the biggest contributions that I made to Vitess open source, and it was a project that took us around 3 months. But now, like everyone who wants to adopt Vitess in AWS should be able to deploy a cluster there that embraces the fact that you have multiple ACs. So after we did these changes, we took the time to migrate our topologies to have dedicated console clusters. So you can now see that each topology have a different console data center. Also, our Vitess deployment now have cells that maps to ACs instead of having a cell for the whole region. This has a pretty neat property. The failure domain and the blast radius of our Vitess components has a one-to-one mapping to the physical infrastructure. It is super clear what will be affected when we have AC failures. And we've been in this setup for about 6 months now. We migrated everything, and we are already seeing benefits. So a couple months ago, we had an issue with an AC during backup times. And we discovered that when backups are happening, if the local topology is not available, backups will fail in Vitess. And the very cool thing is that this time, first, it didn't affect our SLO for backups because the other ACs were fine, and this was just contained within one cell. And the other like pretty cool thing is that now we discovered this new unexpected failure mode. We are able to fix it. We are not going to run into this issue again. But from our client's perspective, this was completely transparent. We didn't do this project for performance reasons, but it also unlocked some performance gains. So given that now that ACs are a first-class citizen in Vitess as well, we can have logic in VTGAs that know when they're routing to a replica to prefer a replica that is in the same AC if that is possible. So some tables at Slack use replica reads heavily. And for this kind of table, this avoid an extra network hop in the query serving path, which had latency gains and also some cost reductions because AWS charges you when you cross ACs. In this graph, you can guess when we deployed this change, and it was like pretty neat performance win, where we got 300 micros back in the P50 of all requests to that table, which was significant for us. Last, I want to start closing with some of kind of the key lessons that we got along the way in this journey of scaling our Vitess cluster at Slack. First, I think it is important to have in mind that complex systems are simply dangerous. And here, I mean fundamental complexity. When you are running systems that need to have 10 million users connected at the same time, the infrastructure to support that has some complexity that is not incidental. And then, when you have that, when those systems fails, the consequences are very high, and basically it's like money that is being lost. Over time, it is natural that you will construct multiple layers of the defense against those kind of failures, including redundancy, backup systems, and also human processes that make it safer to operate those systems. But what is more interesting to us is that in these kind of systems, catastrophe is always just around the corner, especially when there are changing so rapidly and it's just not feasible to protect from unexpected failures. So you kind of have to embrace this fact. It's not enough to defend against failures. You also have to be ready to make sure that you can tolerate those failures and that it's not going to affect all your infrastructure. So one thing that is really important for us here is that these bullet points are not actually from me. And they are from a paper 20 years ago from a doctor. And it was talking about failure in hospitals and in the health system. So I found it pretty remarkable because to me, if I didn't tell you, I think all those bullets apply one-to-one to distribute complex system. But in fact, they come from a different field. And then I think this led us to think that in our industry, sometimes we feel that we are always on the edge of everything and that we are always solving super novel problems. But in fact, there are many lessons that we can get from other industries. And I think to us, it's really important that you have kind of humility towards this kind of complexity, and we reach out to other fields and learn from their experience. And with that, I think that wraps up what we wanted to share today. Also, just a quick thing, if you are more interested about Vitess, there are many talks that are happening this week. These are some of them. Thank you very much. And if you have questions, we are happy to answer them.
Question here. Are those Slack-issued kicks you're wearing?
Sorry?
Your sneakers?
Yeah, so we
Nice.
match. But you can find them online.
Questions? Anyone?
So did you have a reason to increase because your size grew?
Sorry?
The data size growth.
Yeah.
Did you have a need to increase the number of shards, and then how did that work?
Yeah, so part of, again, scaling our fleet is like doing capacity planning. And again, as part of capacity planning from time to time as team, we decide, OK, maybe we need to reshard, again, a key space, so a set of table or database. And again, that's something that Vitess is very powerful because that's done, and let's say, that's something that already provided out of the box. So there is very little kind of operational overhead to do that.
Can you tell more about why it's not run, why you decide not to run Kubernetes? Why it's not suitable for Kubernetes cluster? Why AC2?
Yeah, so you can run like Vitess on Kube, and again, where let's say Vitess is cloud native. We just don't run it yet for kind of historical reason. So there are a few services as Slack that are again starting to move on Kube. We're not there yet because we are right now prioritizing other work.
With respect to storage, how do you manage a node failure, and how do you bring back whatever storage was at that node at the time?
So we use an open source tool called Orchestrator. So all Vitess shards are a MySQL cluster, and they are watched by Orchestrator. So when there is a master failover, there is an automated process that chooses another master and promotes it as master and notifies Vitess about that. Backups. That's a good one. So we are using Ghost, but because in Vitess we have like now thousands of shards, we built an internal tool that orchestrates schema change. Sorry, backups are built in Vitess. So Vitess provides you the management to be able to take backups of your shards, and we use that. Schema changes, yeah.
Another thing that we want to say, well, we are hiring. Also, like we added to those slides, like a very short appendix, like some configuration setting that we use in our setup. Those are the results of like several years of tuning. So we just wanted to share them with the community so you can benefit as well.
In your initial, sorry, I'm over here. In your initial infrastructure, you said that you wanted to replicate across AZs, so that's why you made the cells go across AZs. Why did you want to replicate like that?
Across AZs?
Yeah.
For durability reasons. So we want to make sure, because as Guido mentioned, like our durability as Slack is not on disk. So we rely on replication for durability. So if our replicas were not in different AZs, if you lose one AZ, you could have data loss. Yeah. Does that answer?
So again, if you run, again, semi-sync with one ACK, if let's say a master in USD 1A, USD 1A acknowledge, yes, I have like your transaction, it means that it's been already replicated on another data center. So if that data center just blows up like in 1 second, we still have that right somewhere.
Hi. Yeah. I wanted to ask you if basically your applications, I mean, the replicas are just read-only replicas or also multi-master replicas?
No, so the replica are just read-only replica. So again, we don't want to have replica ahead of the master because that will impact, again, then like topology changes, consistency, and so on. Yeah, so all replica are technically the same. Of course, we're running with semi-sync, so we might have like a bit of drift between all of those. But again, that's expected. Usually when we, again, we want read after write consistency. Like right now in Vitess, you can just do it by querying the master, and you can specify that. We are also evaluating to extend in Vitess to exposing the global transaction ID that a replica has. And then every time that you do a write, you get back in the client a global transaction ID. And on the next read, you can say, hey, Vitess, like a query, whatever, but please use a replica that is at least at this point in the transaction log.
So quick question, you mentioned that you're using EC2 on AWS and then K8 on top of it. Is there a reason you're doing that instead of just going with EKS or a Kubernetes service? Yeah,
I think we replied before, but let's say that we are now kind of, let's say Slack is onboarding like new services to Kubernetes. And again, we're not there yet. We want to solve maybe a couple of other problems before like moving to Kube, but that's definitely on our roadmap.
What did the transition look like going from your initial single topology to the multi-topology? How automated was that, and what did it take to do that?
So the good thing is that because we treat like all our instances kind of like ephemeral, when all the code changes were ready to support that, we deployed the console, the new console topologies, we created the new cells in Vitess, and then it was just a matter of recycling all nodes in the fleet. And then when they come up, they register to a new cell, and then that was it. So actually, like the big effort was just making Vitess ready for that, but deploying it, it was a bit time consuming, but recycling all the hosts, and that was it.
Another thing that we didn't mention for the people that are still here are like tons of stickers if you want to take when you go out.
Thank you.
One more question.
One more question.
Ah, one more question? Okay.
Also, we are hiring.
Hello, so I have a question about the replication. You just mentioned you would have the semi-replication. Is that across data center or just within single data center?
Can you repeat, please? Sorry.
So you mentioned that you would use the semi-replication to do the replication, right? But is that only for one data center or it's cross data center? If it's cross data center, would the latency be pretty high?
Yeah. So it's cross data centers in an AC, but we don't have semi-sync between regions.
Yeah, in a region.
So semi-sync turn on within a region.
So usually we have, let's say within the same AZ, you have sub-millisecond latencies. Across AZ, you usually have milliseconds latency. But we don't do cross-region replication yet.
OK, cool, thanks.
Thank you.
So you said you don't do cross-region replication?
No, we don't do it. We don't say you shouldn't.
Yeah. Does Vitess give you the ability to do like asynchronous?
Yes.
So you can do async cross-region, but semi-sync local?
Exactly. So again, I don't know if it's kind of best practice, but I will suggest exactly what you said. So you usually do semi-sync within the same region, or maybe even like close region. Mm-hmm. And then, I don't know, if for, I don't know, disaster recovery, we do disaster recovery in another way, but like if you need to, again, have asynchronous replicas in Sydney and your data center is in Europe, you can do that. You're just going to pay probably 150-second round-trip latency.
So do you basically define in each cell, like semi-sync to these cells, or?
We define semi-sync between different cells, but same region. Okay. And then the other clusters that are in different regions, they don't know about each other.
For us, are independent. Mm-hmm. But you can do that.
Yeah. Cool. Does that answer your question?
How many master nodes and replica nodes you have?
So at the moment, like hundreds of masters.
Yeah. Thousands of nodes, but we cannot go too much into details of numbers. Yeah. Thousands.
Yeah.
Could you just on the new architecture just step through the mapping of cells to availability zones just
really quickly? Yeah. So in the new architecture, this is how it looks. So we deploy the global topology in the region across all AZs. And then we create cells for each AZ, and those cells map to Vitess cells, and within those cells, deploy all Vitess components. So the cell is like the whole failure domain for.
Okay, so your fault domain in that sense is within the AZ, and then to make sure that the data is resilient. How do you within that? How does the data stay across that fault domain? Like if there is a failure within that, I was trying to work out how that.
So there is semi-sync between like that's allowed. Like for replication, they cross cells.
Okay, so it goes. So you basically affinitize across the cell from an AZ, and is the guarantee sync to sync? It's a synchronous guarantee.
Yeah.
So your one sync is across the AZ.
Exactly. So that's for durability purposes. Like we need to make sure that again a master before saying to the client, hey, yeah, I have your transaction. That transaction has been replicated to another physical location.
Okay, and that's to another fault domain.
Another cell,
Yeah. Okay, that's very helpful.
So if let's say everything explodes in USS 1A, we still have data in other places. The global topology? No.
It does not apply, but the good thing about the global topology is that it's only required to bootstrap the other components. So our idea is that if a global topology is partially unavailable because there are issues between AZs, that only affects bringing up new things, but not normal operation.
Okay, so so then how long does it take to get the global topology back online? Does it take like?
In case that it goes like down, I think that will depend of like the kind of like failure. For us, it's like behind the scenes, that's a console cluster. We haven't had to recover like from an entire failure there,
but again, we have another team that manage kind of key value like locking service and service discovery. Again, they do backup. Let's say regularly. So again, for us, as the global topology is not on the serving path. Like we wouldn't be impacted.
Yeah.
Like we will be impacted like if we need to bootstrap again another cells or like
that was my only question.
New mitigation and things like that.
Cool, thanks.
Cool.
All right.
Okay, thank you very much.
Thank you.
Thank you.